Okay, so Sanjay will tell us about permutation invariant matrix models and natural language data.
Thank you very much, Vishnu, and thank you very much to the organizers of String Data. It's a great pleasure to be speaking here. Indeed, it's a very interesting conversation that is going on between AI and string theory, where we are applying machine learning techniques to study string data. And we heard some inspiring talks on the topic this morning or this afternoon. Kind of, it's natural, within this conversation to ask if we can apply sort of string theory ideas, symmetries, conversely, to learn something about artificial intelligence tasks. So here, I'm going to be thinking about natural language tasks. So this is a conversation that started in 2017 with colleagues in computer science, Dimitri Kartsaklis and Manu Sadrzadeh, who are computer scientists who are at Queen Mary then and are elsewhere now. And this was followed by a paper in 2018 and a further paper with Manush Sadrzadeh again and Louis Sword, who was master's student here and now PhD student. And now I have some active PhD students working in this area, both on the data science side and the sort of mathematical side. So indeed, the mathematics that is involved is sort of group theory of large N. And there's some of the themes of symmetries that we heard about earlier, you will see at play as well. So I'll refer to these papers by their year. And so this is the story. So basically, we're studying something rather generic that could come up in many situations where you have an ensemble of matrices, which is an interesting collection, where A is an index that runs over the ensemble. For example, in my example, there'll be about 200 words we're thinking about. And for each word, or perhaps 1,000, depending on the situation. And for each word, we have a matrix, the size of which is D, and D can be between 100 and 2,000. And turns out that in the field of what is called compositional distributional semantics, initiated by computer scientists Kirker, Sadrzadeh, and Clark at Oxford in 2010, there are techniques for generating interesting ensembles of these matrices, depending on their grammatical structure. And you can also generate sort of higher tensors for a given word, depending on, again, the kind of grammatical structure they have. And so this LMT program, this linguistic matrix theory idea, is to develop random matrix theory, in particular permutation invariant random matrix theory, to study the statistics of these matrices that are being generated here. So some of the theoretical developments we have made in this sequence of papers, we have looked at enumeration and construction of permutation invariant matrix observables. We have looked at the general permutation invariant Gaussian action, and we've looked at, there's some computer code for making computations with these actions, calculating expectation values of polynomial functions when you insert them in your path integral. And recently we have looked at a large N factorization property for these observables. And on the applied side, there's statistical physics, and there is computational tasks associated with natural language data. So on the statistical physics side, we have looked at approximate Gaussianity. This was the focus of the first paper and in the 2019 paper. Now, when I started looking at approximate Gaussianity, I thought, well, this is as applied as I can get. But my colleagues told me that, how can we write a paper without solving any tasks? So slowly, the program also moved towards concrete natural language tasks having to do with distinguishing synonyms, antonyms, hypernyms, and hyponyms. This is in the 2022 paper, and along the way, I hope I'll have time to tell you what I learned about what these are. So the distinction between synonyms and antonyms is an important challenge in distributional semantics. And this kind of approach based on permutation invariant matrix observables, I can try to convince you has something to say about that. So this is the outline. We're going to have an introduction to compositional distributional semantics. How do we associate vectors, matrices, and tensors to words? And how do we argue for permutation invariance as an interesting symmetry in this setup? And then we're going to look at Gaussianity in this permutation invariant sector. And we're going to use sort of ideas from random matrix theory along with ideas from particle physics. And then we're going to describe a 13-parameter model, which is the most general Gaussian model with permutation symmetry. And the observables turn out to be described by graphs. So that's a nice combinatoric structure. And so there's kind of an interplay between representation theory and graphs, and sort of that sort of connected by a sort of Fourier transform. Using that transform, one can compare the predictions of the theory to data. And I'll show you some of the results from that comparison. And hopefully I'll have time to show how this framework is useful for concrete tasks. So distributional semantics is the study of word vectors. So the idea is that the meaning of a word is captured by the context in which it occurs. So you construct vectors for words from frequencies with which they occur in the vicinity of a specified set of context words when you look at a collection of text. So for example, imagine you're looking at a collection of books and you take pet and feed to be two context words. Then you look at your word of interest, W, and you say, how many times does the word W appear in a 5-word window of pet? So within left or right, or within 5 words of the word pet. And that's a number, it's a frequency. And then you do that with the word feed, and you get a vector, one for the co-occurrence of W with pet, one with feed. So the idea is that these vectors know something about the meaning. So for example, cat will occur frequently with pet and with feed because a cat is a pet and you feed it often. Likewise, dog. But the word baby is not a pet, but you feed it a lot. So probably these are the kinds of frequencies that you might see. So this is represented in geometry by these vectors and the fact that dog and cat are similar. There's a notion of word similarity that computational linguists are very fond of. And they look at different measures that you can put on the vectors in order to assess similarity. So the dot product, or the angle between these vectors, is a measure. Compositional distributional semantics is a framework where now beyond vectors, we can have sort of tensors and matrices associated with words. And the idea is that with this richer framework, you can construct a vector, which represents the meaning of a sentence. But the way you get the vector for the sentence, it comes from combining the tenses for the different words appearing in that sentence and then contracted in appropriate ways. So that's the essential idea of compositional distributional semantics. So now you have words associated with vectors, matrices, or higher rank tensors. So in this linguistic matrix theory, we started studying the statistics of matrices that are associated to adjectives. It turns out for adjectives and for intransitive verbs, you get matrices, transitive verbs, a higher rank tensor, and so on. So you've got a collection of matrices and you would like to analyze that. And so we use ideas of random matrix theory. In particular, we just think of that as giving us some probability distribution over large matrices. And as we are familiar with, following Wigner and Dyson, RMT has been applied to many, many systems, complex nuclei, molecules, chaotic systems, financial correlators, biological networks, and so on. So the simplest random matrix theory, we're just thinking about an integral dm into the minus trace m square, where m, if you transform it under unitary symmetry, this action is invariant. So the unitary invariance in physics corresponds to basis changes in the Hilbert space. And is this the right kind of invariance in linguistics? Well, we argued that it's not the case. And the reason for that is that, you have vectors, for example, P and Q. As we said, sometimes you have word similarity, which comes from angles. Angles are obtained by looking at dot products. That certainly is an ON invariant quantity. If I transform this by ON and this by OD rather, and this by OD, which is a continuous symmetry, this is invariant. But in computational linguistics, people often look at expressions like this, which are not OD invariant. So they're trying to extract information from vectors which is not invariant under continuous symmetries. For example, for one of the things that people study, you could have two different word vectors, P and Q, and here's a formula which you can study as some function of P and Q. And this has been argued to measure entailment, whether the word P entails the word Q or not. And that kind of expression is no longer invariant under OD, but it is invariant still under permutation symmetry, which takes PI to P sigma Y, QI to Q sigma Y. If you do that transformation, it's still SD invariant. So it's kind of the general kinds of things people look at seem to be looking at information which is SD invariant. So we started, therefore, looking at matrices in this paper, and our colleagues, the computer scientists, constructed matrices for adjectives extracted by analyzing some corpus of text. And the way they did that, first they built vectors for nouns. For example, if you have a noun such as car, you build a vector along the lines I described using frequencies. You have a composite noun or a noun phrase, black car, you can get another vector for that sort of noun phrase. And then the idea is that you want a matrix for black, which will map by matrix multiplication, the vector for car to the vector for black car. So they use linear regression to find the matrix for black, which ensures that in general for noun X, if you apply the matrix black, you get the vector for black X. So these are some traditional techniques in distributional semantics, and in particular in compositional distributional semantics that has been developed for some time. There are also other ways of developing these matrices involving machine learning, and I will mention some of that towards the end. So these guys, built a collection of matrices. I think there were about 300 or so. Their matrix sizes were between 300 to 2,000 in steps of 100. And for example, if you look at a matrix element in the 2000 by 2000 case, here, let's look at the value, just the value of the matrix element. I plot the value of that particular matrix element, and I look at how many different words have that value in a particular bin here, and you draw a histogram, and there's some kind of indication of Gaussianity. So let's remember something useful about Gaussians. If you have a single one variable Gaussian, there's a probability distribution. It is quadratic in X. It's a quadratic expression, a linear and a quadratic term here. X is your random variable. And this distribution has two parameters, mu and sigma. And you can calculate expectation value of X and X square in terms of mu and sigma, which are the parameters of your model. And then, of course, higher order moments can be calculated in a similar way. And there are some functions of mu and sigma. So what you can do, if you want to study Gaussianity in a very simple way, is have some data set and you look at X and X square experimentally. You match that with these equations, and then you determine a probability distribution. In other words, you determine mu and sigma. Then you can go ahead and say, okay, I calculate using these theoretical formulae, what are the expectation values? And then we ask whether these guys match the data. So experiment X square, experiment X cube, and X to the 4, and so on. Do they match the experimental data? So that's the basic idea behind the Gaussianity tests that we do. Except here, we don't have one variable. We have a matrix variable, D by D. D could be large. And here in this paper, we looked at the simplest kind of model where you had, if you want permutation invariance, you look at the diagonal elements and you have a quadratic term. If it's permutation invariant, you're going to sum all of them to give a permutation invariant quantity. And separately, you can deal with the off-diagonal terms, where I less than j, you can mij square type terms and mij mji type terms. So in this kind of 5-parameter model, it turns out there is 2 linear terms, one for the diagonals, one for the off-diagonals, and then you have 3 parameters for the quadratic terms. So this kind of model can be solved. It can be solved quite easily because essentially, well, by solve, so you can calculate the path integral, you can calculate correlators. And the reason it's easy to solve is because you've got these sort of decoupled integrals here. And then you've got d times d minus 1 decoupled integrals, one for each pair. So you can solve that, and you can calculate in terms of the parameters of the model, these linear and quadratic expectation values. For each of them, these are the theoretical, these are the quadratic linear expectation values. For these linear and quadratic expressions, you can get an experimental average, which is for each of these functions of m, you take that function, you sum over the words, and you divide by the number of words, you get an experimental average. And that you set to be equal to your theoretical average in order to set up the parameters of the model. And you get some parameters. And then using that, you can predict the sort of, if the Gaussian model is correct, you can predict what the higher order moment should be. So we looked at a couple of these things in the 2017 paper. So for some of them, the theoretical and the experimental values were within, I don't know, 40% and a bit. And so that sounded sort of broadly within the realm of perturbation theory. Whereas for others, the ratios of these quantities were quite small, so that we considered to be rather far from sort of the prediction. So the natural next step would be to consider not just that 5-parameter model, but the most general quadratic action that you could think of. So there were 2 linear parameters. Turns out you can classify these permutation invariant functions of matrices using graphs. Essentially, it's got to do with just having a bunch of indices which correspond to nodes, and you have m's which correspond to edges. And for each graph of this sort, for example, mii squared, this is some which is permutation invariant. And for that, this m corresponds to mii. This is another mii. If you have mij squared, you have a graph like that. So there are 11 such things. So you can write down an action which involves these 11 quadratic terms. It's not too obvious how to solve such a thing. However, you can make progress and solve it using representation theory techniques. Representation theory tells you that you have to think about these matrices as forming a representation of SD. And the representation is just VD tensor VD, where VD is the sort of fundamental or natural representation of SD. And here you're just acting diagonally on these 2 indices. This comes basically from saying that if I want invariance where my usual continuous symmetry is replaced by permutation symmetry, where these are permutation matrices, this is how Mij transforms. You just permute each of these indices. So that amounts to studying the representation theory of VD tensor VD. And that tensor product can be decomposed. And there are 2 copies of the trivial representation, 3 copies of this representation in terms of Young diagrams, 1 copy of this one, and 1 copy of this one. So basically, there's this multiplicity of 2, this multiplicity of 3, this multiplicity of 1, and multiplicity of 1. And that essentially leads to an action where you write down some variables that are not the original VD tensor VD variables, but rather transform according to each of these irreducible representations. And there are some appropriate Clebsch-Gordon coefficients. So using these nice rep theory variables, it's easy to write down the action. These are the linear terms. And there's basically one kind of quadratic term for each of these E-reps that appears. The trivial one, the one that I call VH, and then the one I call V2, and the one I call V3. And these coupling constants in the action, the only non-triviality now left has to do with these multiplicities. Basically, you have one 2x2 matrix and one 3x3 symmetric matrix, and 2 1x1 matrices, essentially having to do with these multiplicities here. So that gives you a new way to parameterize the invariants, not in terms of graphs, but in terms of rep theory variables. And using these variables, you can work out in these rep theory variables, what are the 2-point functions. Essentially, as you would expect, they are diagonal in terms of the E-reps. If you have distinct E-reps appearing here, you're going to get 0 because of the delta function. And if you have distinct multiplicities, alpha and beta, then you're going to get inverse coupling matrix. And these state indices, you're just going to get delta AB once you have chosen an orthogonal basis there. So for this reason, the 2-point functions are very simple once you go to this rep theory basis. And once you've done that, you can write down the 2-point functions for the graph theory observables, by doing the change of basis using Clebsch coordinate coefficients, and you get some expressions which are functions of these coupling constants, mu for the linear terms and lambda for the quadratic terms. And then you can also get expressions for the cubic terms and the quartic terms. And out of that, you can do what we did before, which is that you take the linear and quadratic expressions, you put in the data from experiment, determine the parameters, and then you feed the parameters in these theoretical sort of expressions, and then you compare. So you compare, you get theoretical values for these some cubic and quartic expressions. And I don't want you to look at the numbers, but look at the ratio. For some of them, it's around 0.6, the kind of thing we were getting before. Sometimes it's a bit less, but for a good number of them, the ratios are near 1. So that we took to be saying that there's good evidence for approximate Gaussianity in the system.
5 minutes.
Okay, lovely. So by the way, when we do these comparisons, sometimes it is useful to, instead of taking a ratio, we found it useful to take a difference divided by the spread in the data. And that gives a similar sort of answer that you get. For a lot of the observables, you get these ratios to be quite small, which means that this difference correctly normalized are quite small. So now I want to get to the sort of natural language tasks aspect. So now you have this interesting permutation invariant observables, which perhaps capture, we have evidence capture some Gaussianity. And now can we do something useful with them? So here we looked at a set of matrices that were constructed using machine learning methods for a set of verbs. There's a standard data set called SimVerb 3500. There's 3500 verbs there, 3500 verb pairs there, which are organized according to whether they're synonym pairs, antonym pairs, or these other types of pairs. So what you can do with each of these verbs, so A runs over the verbs, little a runs over a set of observables, one of these polynomial functions that we were talking about. So for each verb, you can take the value of that observable minus the experimental average. So that's a vector associated with each verb. So much like you had vectors of frequencies before, now you have vectors of invariant functions associated with each verb. So you have this vector, you could choose to work, your matrices are quite large, but you could choose to work with 13, linear quadratic variable observables, or 20, or some small number of such observables. And you can study the distribution of these observables as you scan the set of verbs. So you can get, for each of these observables, you can get an experimental average, you can get a deviation for that observable. And this way, you get a feature vector for that verb, which is constructed using invariant functions. So it's kind of naturally factors out this permutation symmetry. And then, so what do you do with these things? If you've got these new kinds of vectors now based on invariant theory, you can write down a inner product. This is a very natural inner product where you treat the distinct functions, these distinct graphs, as orthogonal. And that's one natural inner product. There's another one natural inner product that comes from statistics. There is a kind of the inverse of the correlation matrix here that you can put in, and you get another natural metric. Okay, so there are two natural metrics you can play with. And then now you can take, what is the angle between these vectors? So you're given two verbs. You can take their dot product, correctly normalize it, and you get a cosine for a pair of verbs. And then you might guess that, synonyms, for example, should be more aligned than antonyms, which should be kind of further apart in this space. And turns out that expectation works out, that if you look at pairs which are synonyms, you look at the cosine, this is 0.28. For the average over the antonyms, they are 0.093, no relation, they are in between. And using that, you can sort of say, okay, this is the range of cosines, this is the mean for the synonyms, mean for the antonyms, there's an appropriate barrier in between. Let's say I'm going to predict everything here in my data set to be synonyms, and I predict everything below here to be antonyms. How well does that sort of do in this task? And you find that you get sort of, depending on which kinds of discrete choices you make in the system, near 56%. So they sort of above random guessing. And then I won't really have time, but for some of the tasks having to do with hypernyms and hyponyms, There we don't look at angles, rather we look at the lengths of the vectors. And again, we do a sort of task of distinguishing between, in a pair, whether something is a hypernym or a hyponym, distinction task, and there we get sort of success rates between 62 and 67%. So basically, this suggests that, what you would expect, that observables that kind of factor out the redundancies are capable of capturing meaningful information. So these permutation invariant matrix observables, that lots of funky, nice graph theory mathematics around them. They show evidence of approximate Gaussianity in natural language data. They show promising results in natural language tasks. And a future direction is to use, for example, machine learning techniques to explore the parameter spaces, the choice of observables, and so on, which you can explore for the future. And just final observation, these investigations of Gaussianity and statistics can be applied very generally whenever you have a collection of real world entities, genes, proteins, whatever, such that each entity can be associated in a meaningful way using some AI techniques or whatever to a matrix, which leads to a coherent collection or a coherent ensemble of matrices. All the things that I discussed, you can explore. And if you want to chat with me about any of this, I'll be happy to discuss either now or afterwards.
Thanks, Sanjay. Question from David?
Yeah, hi. Because you're taking a sample of these matrices, is there any sense it's Gaussian because of a central limit theorem?
That's a very good question. In fact, the central limit theorem is probably some reason behind the Gaussianity that we are seeing. But I think that has to be developed because, developing central limit theorem in this context of permutation invariant functions of matrices, I don't think this has been done. So it's certainly something to explore.
Sven?
Yeah, thanks for this interesting talk. Is there, are there benchmarks around, where one can compare results to?
Yeah, this is one. Thank you for the question. It's in fact, the nice thing about working with computer scientists is that they are very intent on very particular tasks, very particular data sets, and so this kind of synonym antonym distinction. There are certain, the precise tasks that we formulated and we addressed, they were not exactly the ones that the literature has addressed. There's a few papers on synonyms and antonyms. Generically, synonyms and antonyms is deemed to be a rather hard thing in distributional semantics because the frequencies with which a synonym, a pair which are synonym, will occur in similar contexts. But if they're antonyms, they might also occur in similar contexts. So just from frequencies, so you have to invent somewhat subtle measures. So it's not such a very, very actively studied field, but there are a couple of papers that we are trying to compare with.
And how well do you do?
So I think the 67% that we got is competitive, yeah. As I said, it's not the exact same task that they have looked at, but yes, but it's something
get an impression.
we do reasonably well. Yeah.
Thanks.
Other questions for Sanjay?
I can do another one, but it seems terrible since he's next door to me. But I would just say, this thing where you have all these terms in your matrix model, and then you're comparing from looking at the higher moments. It looks like this would be an ideal thing to do a Bayesian analysis with, right? And then come up with a distribution on the coupling constants from applying Bayes from the data. But
to be honest, I sort of agree, although I don't fully understand the statistical theory behind these estimates and so on. But I think I agree. One has to think more carefully about how to do these comparisons in a way that statisticians would be fully happy with.
It's a natural Bayesian problem, basically.
Yeah.
Given data to then put probably distribution on the parameters. But anyway.
Yeah. I guess you can ask, I guess given the data, what's the most likely
You
set
can
of
ask most
parameters.
likely, but even better, you can even come up with a distribution.
I see. Thank you. Thank you for that.
Other questions? Not thanks, Sanjay, again.
Thank you.
There is one question. Arge, question?
Yeah. Hi, Sanjay. Thanks for the talk. So probably very nice question. So as you're saying that for this Gaussianity, I mean, at least whatever you're done for seems to be, and that you're saying that it can be generalized, but so far this is for, let's say, English language, right? So you can go to other languages.
Certainly.
And can you classify, I mean, do you think that you can classify languages in type of, you know, I mean, who knows, like deviation?
Certainly. Well, you know, I guess certainly, you know, the set of parameters, the values of the parameters that you get, you know, you would, you know, for each language, you would get a set of parameters. And I guess you would want to understand in what sense you've got two comparable data sets. I guess if you take as large a data set as you can get in English and as large as you can get in French or Hindi, then look at the limits of large data sets and see what values of parameters you can get or what kinds of non-Gaussianities you can get. Yeah, certainly, I think it's a tool for comparing different kinds of data sets coming from different languages, or even within English, coming from different ways of constructing the data, different kinds of corpora. Yeah.
So one more related one to take short time. So as you're saying that this can be generalized. So let's say I have coding languages, let's say Python or C or C++, right? So you can run this thing in there as well, right? But now for the same task, you will have same you should have same distribution at same meanings for different languages as well in this case. Because all of the...
So one key thing is this compositionality. I agree. It is very, you know, basically the starting point is the construction of these matrices. And I think it is one has to explore to what extent this idea of building a matrix, such as, you know, we had, you know, car, black car, as long as you have some analog of the notion of noun and composite noun in any setting, and then you have a notion of some modifier like adjective. So this is the first step that has to be thought about. Exactly. You know, I think as Mike was saying, building the data, a good data set is one of the starting points. So once one has a good, meaningful data set that you trust, then yes, there's a machinery you can run with it.
Okay, excellent. Yeah, I was just thinking that then one can even look for, you know, simple versions of codes. I mean, when Python is more closer when higher level languages and also.
Yeah, I'm very happy to discuss this. Please, you know, if you want to discuss, I'm happy to chat about this. Yeah.
Sure. Yeah, thanks for the love.
Okay, let's move on to the next speaker. So maybe share a screen.